Welcome everybody to another episode of the Puget Systems podcast live Q&A show. This week we have one of my most favorite people to talk to, Dr. Don Kinghorn, our scientific computing advisor here at Puget Systems. And from what I understand, Don, we have there might be a bit of a rant today, and then a little bit of a discussion on the incredible performance that you're seeing from the A100, which is, as I recall, the new Tesla card. Is that the right kind of thing, or is this more of a re kind of is it a Quadro, or is it more of like the Tesla compute card?
It's like Tesla.
Okay.
But I've got to hang on a second here because
sure. Uh-oh.
Let me. Okay. Are we good?
Yeah, we're good.
Oh man, I've got this crazy audio thing that's just like blown up.
Do you have the YouTube stream open? Perhaps.
Where is it? Oh, it might be. It's on another browser. Oh man, maybe I do.
Thank you for your patience while we had to handle these.
Yeah, I'm sorry here.
No, it happened. I do it to myself a few times as well, so it's all right. Probably had the link open to share it earlier today, and now we're live, so you're hearing me 10 seconds later.
Yeah, that's exactly what I'm doing. Oh, there we go.
Is this better?
No, I'm still hearing you 10 seconds later.
Yeah, it's definitely the stream then. Somewhere.
Hey. Oh. Yeah, I'm still. Oh man, I'm sorry, everybody. I have to fix this before I go anywhere because.
Oh sure, no, it'll be very distracting.
This is absolutely insane.
A quick Band-Aid. You could go into Windows, your sound settings, and just mute Chrome altogether.
Yeah. Okay, I'm not on Windows.
Oh.
Okay, hang on. There's got to be something here.
Sure. That's okay.
This is driving me crazy. Wow, this has got to be coming from Chrome, right?
Most likely, yeah. You've got YouTube open somewhere, or Twitch, or Facebook.
Let me. There. Let's see. Did it go away?
Did you hear yourself?
Oh, hey.
Hey, all right. Cool. There we go.
I'm sorry. This maybe it has something to do with my screen sharing or something.
Oh no.
Yeah, I have multiple browsers. I have Chrome and Firefox running, and 40 tabs open because my work system here.
Yeah.
Well, that was a great way to start.
Yeah. Hey, it's all right. When we deal with technology, you get technical problems, so it's all good. But yeah, welcome. Thank you, John, for Dr. Don, for taking time out of the day to join us today, talking about couple big ones. I think, or at least to me, this would be very interesting. Docker without Docker, and then the A100, which we were saying is the new Tesla card, sort of, but they seem to be dropping the model names like that, like they did with the Quadro. It's not a Quadro anymore. It's just
they have them in different classes now.
Mhm.
You know, they basically, there's compute, which is what, you know, Tesla used to be. You know, it's officially compute. Then you've got like Quadro, which is now I think professional. They just call it professional or something.
Okay.
And then you've got gaming or something like that.
Yeah.
You know, consumer or something. I'm not sure.
Yeah.
But
it's hard though, because it's like, if we talk, well, I guess, you know, the RTX 6000, I guess you just kind of just assume that if it's in the thousands range like that, then it's Quadro, and then
Quadro, yeah.
And so in this case, I imagine then stands for Ampere, right?
Yes.
The new architecture for them. So cool. Well, where would you like to start then, Don?
Well, I think probably talking about the A100.
Sure.
That's I've said this before about Nvidia GPUs, but it's the most incredible computing device I've ever used.
Yeah.
Okay. I mean, it's amazing, and you'll see why. It's just crazy good. I do want to talk about Enroute. I'll probably talk about Enroute in more of a kind of a separate thing.
Sure. Like a different stream, or just later on?
A different stream, yeah. You know, I'll mention it because I used Enroute for running containers that for doing all this benchmarking, and it's my default. It's been my default container runtime for a long time. I haven't used Docker for ages.
Wow.
Which is actually, that's kind of interesting, especially talking with you, because when I was first doing Docker, you were doing the Twitch stream. And I wrote a whole series on Docker, and you know what it was and how to use it, and specifically how to set it up so that it's actually kind of usable for on a workstation for an individual. But one of our streams became a reference document at Nvidia. It was largely because the people that were working on Docker and containers and stuff there got tired of answering questions. And this is just a little funny story.
I love it.
But so a few of my posts became just like official references at Nvidia, and then
so cool.
at GTC around that time, I was looking for the Docker guys.
Yeah.
Okay, I was looking for. I went over to the Nvidia booth, and I was going, and he's going, there's a company here that's doing really cool stuff with Docker, and I think there's somebody over there that really knows, you know, what they're doing, and talk about it. And he was all excited about it because he knew what I was talking about, and he's going, let me take you over there. And he took me over to our booth.
Oh, no way.
It's like, this is my booth, man. It was funny.
Oh, that's cool.
But
it's always excited to know, like, when something casual like that, like we weren't trying to do anything really super professional. It was just kind of a rundown of what Docker is and like the technology behind it and how it's helpful and all that stuff. And then to know that the big wigs in the thing is like, that's really neat.
One of those streams was really helpful for people trying to understand what, you know, containers were all about, and you know how Docker worked and stuff. But I haven't used Docker for ages.
Right.
In fact, a lot of people are not using Docker anymore.
Okay.
You know, you've got all these different container runtimes, and Enroute, I really, really like it because it gives you a container sandbox. Okay, so it's really friendly for like an end user. It's not their intention. They're really working on it to be integrated with big clusters and supercomputers and stuff like that.
Oh, cool.
For things like Slurm, you know, with resource managers, it works really, really well there. And I have used it kind of in that context with Jupyter Hub, Jupyter Lab, and Jupyter Notebook server. It integrates in with that really in a really nice way, because otherwise it's really a pain to get containers into something like that. So it's very powerful. But but I want to champion it a little bit as for like an end user, because oh man, it's really a nice way to do it. It's simple, and it's like really what you want if you want to run a container like as an application on your desktop.
Oh, cool.
Because there's no roots not involved. You own everything. There's a whole slew of advantages. Yeah, I like it, and it's about time that I talk about it. I put a post up last week or so, and I just briefly touched on stuff, kind of gave an introduction to it, and but yeah, I'll be doing more with it for sure.
Yeah,
and I'm gonna start including in my posts where I'm using containers. I'm going to start including like what enroot commands and stuff like that I used.
Okay.
For setting things up and getting things to work, and that cool. That gives a reproducible. That makes the stuff that I'm posting more reproducible for people. They can do exactly what I did.
Oh, that'll be helpful. That's cool.
So
yeah,
right but for the latest use that I made of that,
okay,
was we've had the Nvidia A100s for a while now, but I haven't really we took our time qualifying them and all that, and I haven't been doing much because there were so many other hardware things going on. Oh no!
Yeah, we're gonna mute Don for just a second while he handles the phone call. Just in case it's something personal, we're muting Don here for just a second.
I forgot to turn that off.
Hey, no worries.
That was the wife, by the way, and I always answer her call. It didn't sound like it was an emergency or anything like that.
Okay. We don't want to get you in trouble.
Boy, we're having all kinds of those nice live-ish kind of things today. A little personality in this one, right?
Yeah, that's why I like live content.
Okay, yeah. What I was getting back to, but anyway, all this all these hardware launches, all this stuff. I was like, oh man, let me play with the GPUs. I want to get back to the GPUs. Let me do some machine learning stuff. Anyway, that's going to be that's it going forward. I'm really that's going to be a big focus.
Yeah.
And one of the things that I wanted to do is I wanted to really showcase how amazing these new Nvidia GPUs are.
Yeah.
And I have kind of a soapbox. I've been a GPU computing advocate since it was possible to do it. Okay. And in various contexts.
Right.
And so yeah, I'm definitely all about it. But it's improved so much, and Nvidia just keeps killing it. Every compute GPU that they've done has been like doubling.
Wow.
They've had some intermediaries like Turing and stuff where they didn't have, and Maxwell where they didn't really have any compute versions of those.
Right.
But like going from Pascal to Volta to now Ampere, these things have just been going like straight up to the right.
Wow.
Yeah, you do that a few times, and it's like, whoa, it is up there. And the thing is that it's getting easier and easier and easier to run code on a GPU.
Awesome.
Okay, I mean it's almost simplistic at this point. From like a traditional standpoint, you've got like C, C++, and a Fortran compilers.
Sure.
Nvidia, owns the Portland group, PGI, their compilers.
Okay.
And that's fully integrated, and they've been working on this stuff for a long time.
Mm-hmm.
And they're integrating GPU into those compilers in an easier way than it has been in the past.
Cool.
You've got OpenACC, which is a pragma based, where you give like little directives on algorithms that tell it, okay, this thing can go off to the GPU, stuff like that. They've had that for some time, and it's really quite successful. Some people have done really well with that. They've got a whole slew of standard libraries that people use for high performance computing.
Right.
And you can make those library calls essentially with the same kind of syntax that you would use for calling those libraries on CPU-based system.
Oh,
okay.
Sweet.
So it's getting easier and easier, and they're directly like integrating this stuff in a smart way into the compiler, so that a lot of it just becomes automatic. Okay, so it's
great.
getting better and better and better. Now that's on that traditional end of it. On the non-traditional end of programming, which I'm a champion of that.
Yeah.
You take something like Python. You take Numpy.
Sure.
Okay, Numpy is numerical Python. It's it's kind of a standard. It is actually a standard.
Oh,
the
cool.
Numpy API has become like an accepted standard.
Okay.
And everybody has these things that have some like Numpy compatibility, or they use Numpy data structures and stuff like that directly, and they're trying to standardize that.
Cool.
This is a great effort that's going on.
Yeah.
And the thing is, you've got things like PyTorch, for example, which is one of my favorite. It's mostly Numpy API compatible. So you've got, and this is a machine learning, an AI framework, right? Deep learning framework. But it's got all of the numerical linear algebra stuff in it that you would use for writing any scientific code.
Wow. Oh.
And if you can write your code in Numpy, which is like really easy, right?
Yeah.
Like 100 times fewer lines of code. And if you can do that, and if you can put your algorithm, get rid of loops, put your algorithms into matrix and tensor operations, then it's just like one line to send all that stuff over to the GPU. And performance is just boom.
Oh, you love to hear it.
So and that's where I think the future of scientific computing and programming is going to be more like that.
Awesome.
It's going to, rather than, they're still invest. You've got millions of lines of old Fortran and C++ code,
right? And
they're trying to port that over, and that's why there's a huge effort on the compiler side,
right?
And that's important. But man, I love something like Numpy. Numpy APIs. TensorFlow has a Numpy API. There's PAX, which is a Numpy API. There's a whole bunch of them, and they all work on the GPU.
I love it. It seems like in every industry, every time I talk to anybody on this show, it doesn't matter if it's game development or filmmaking or like this virtual production stuff, scientific computing, everything is becoming so much easier to get into. Like hobbyists can, or somebody who's like, oh, I'm curious about this. I wonder if I could just play around a little bit. You don't have to take 3-4 years of school to figure all this stuff out, and you don't have to become a master programmer. You can I have a graphics card. I have you follow some of the articles you've written, and boom, I can play around. And now I have, is this a hot dog or whatever? And it blows my mind every time the barriers to entry are just becoming so easy to leap over.
Awesome. It's interesting, and I agree with that. There's ways to dive in, and without almost just cold.
Yeah,
and actually do some really cool stuff. There's also a flip side of it. A lot of stuff is so enormously complex that to really understand everything that's going on is worse than ever. but so there's it's kind of gone, the curve has gone up on both ends of this.
Sure.
Yeah, it's but yeah, that's very true. And to be able to use a higher level language like Python with Numpy and write serious code with it that really performs really well, that's I mean, that's just crazy. So I think maybe it's time to look at some stuff. I just finished the testing.
Okay.
And it's amazing. And I've started writing up a blog post, and I moved a bunch of that stuff over to our site so I can actually share this, and you can get a preview. It's not going to go up today. It'll probably go up later Monday. But the charts are what you want to see.
You guys are getting insider info before anybody else on the spot while it's hot, not even hot off the press, before it even hits the press, before it hits the printer. That's amazing. I'm stoked. This is cool. Okay, so you've gotten a chance to really dig into the performance of the A100 in this is your classic mix of benchmarks. I'm looking at the article myself here. I got it on my own site. It looks, you got the Hpl, HPC AI, HPCG benchmarks, and these are pretty much your normal mix of benchmarks, right? I noticed LinPack is missing. Is that more of a CPU thing?
HPL is high performance LinPack.
Oh, okay.
These are supercomputer benchmarks.
Okay.
These are the benchmarks that are used to rank the top 500 supercomputers.
Wow.
In particular, HPL is the traditional one. You usually see some like insane, petaflops and exaflops, whatever. They're talking about. They're talking about solving a dense system of linear equations with a LinPack type of thing. That's HPL.
Okay.
Then there's a new one. The newest new one is Hpl Ai, and that's the same problem. Okay, but it's done in mixed precision. So this is traditional scientific computing stuff. This is traditional numerical linear algebra.
Okay.
What you would normally think of as like high-end numerical computing. But one of the big uses now, and even of supercomputers, is people are doing it for training models. They're doing machine learning on supercomputers now. The supercomputing world has just fully embraced that.
Cool.
Because it was really clear that they need to help with this stuff.
Okay.
Because the computing resources can be enormous, and that's what supercomputing is about, right? This is the crazy stuff.
Yeah.
And Nvidia's killing it in supercomputing. They have their own supercomputer.
Oh yeah.
That they own. That it's the highest performance, commercially owned, company owned supercomputer.
That's cool.
Yeah. Yes. I mean, yeah, it's just great. But let's go ahead.
We'll show this.
Yeah. Let me see. Yeah. Here we go. Okay. This is a little preview of it. I've been debating about the title because there's been a few things like CPU is dead, just use the GPU. Those kind of titles have been suggested.
Right.
And I had a boring one there. Nvidia A100 PCI on Hpl Ai, HPCG benchmarks. That's what I started with. Then I went, I could at least put something in there with a little flourish. This is what's going on here. And in the intro here, I've got the three things that we're talking about in relation to these benchmarks. Actually, you can see the whole thing here now. HPL, that's high performance LinPack. This is LinPack. And it's always been the first thing I ever run on any new computing hardware. It's like, okay, how does it do? What's the gigaflops? How much performance can this thing really do? Because this is an algorithm. HPL is tuned by hardware vendors it's optimized to give best performance.
Okay.
Because it's how they are going to be judged.
Right.
And it's also it's a really good measure for just raw, hardcore, double precision, floating point numerical compute performance. So it's a good measure. I like it. It has critics, and that's why there's other stuff in the list.
Right.
But so there's that. That's a double precision floating point performance. Hpl Ai, the mixed precision benchmark, that's the same thing, but instead of being the traditional double precision, this is a mixed precision with 32-bit floating point. Okay, so single precision.
Mm-hmm.
And there's nothing wrong with single precision. I mean, there was a time when that's what you had, right?
Sure. Yeah.
But this is very important and this benchmark is a better measure for people doing things that, especially like with machine learning, where they're not using, double precision floating point.
Right.
They don't really need it for optimizing model parameters, in some big neural network or something like that. And so that's why it's tagged with AI at the end.
Oh, sure, that makes sense.
And on GPUs, this gives you a huge performance increase when you go to lower precision. On CPUs, it doesn't make that much difference.
Oh, that's interesting. Okay.
Interestingly enough.
Yeah.
Yeah. So, and since most supercomputers have some kind of accelerators now,
right.
And in particular, they have Nvidia GPUs in them for a lot of them. This one really made sense, and Nvidia was not behind. I mean, this is a real thing done by the people at Top 500, and I mean, this is it's an accepted thing. It's not just Nvidia trying to push their agenda.
Sure.
So it's totally legit benchmark, but this is the first time I've used it. I've messed with it at all.
Okay.
And then there's HPCG, and this is high performance conjugate gradients.
Mm-hmm.
And that benchmark was added basically because of criticism for HPL, because HPL just focused on one little aspect of a supercomputer. Okay, but the I/O, the communication, the memory performance, and the overall I/O performance of the entire cluster is equally important, at least equally important. So HPCG is in there to kind of fit that, is to give like a better view of kind of like more the overall performance of the entire system. And it also happens to be highly memory bound code.
Ooh, okay.
So this really is measuring memory performance, and in a big cluster, it's measuring memory and memory over fabric.
Sure. Okay.
So yeah, it's another good one. I really like it. That's a great benchmark. There's a lot of code. There's a lot of problems like traditional numerical simulation where you're solving like systems of differential equations. Okay. So like these, kind of more traditional engineering and physics modeling. A lot of that stuff is memory bound. So the performance is limited by memory performance. And you can throw more cores at it, you can whatever, it doesn't make any difference. And GPUs happen to have just insanely great memory performance. Okay, so that's the benchmark. So this really kind of covers pretty good ground here.
Yeah.
We've got the traditional double precision floating point for hardcore traditional numerical computing, numerical linear algebra. You've got Hpl Ai, which is more appropriate for like modern things where these, machine learning stuff.
Right.
Okay. And then you've got HPCG, which is looking at memory performance and is a good measure for memory bound applications.
Mm-hmm.
So this is a pretty good set, and these three are used now on systems that are submitted for ranking on the top 500 supercomputing site.
Neat. Well, that's
So
cool. Because there's folk out there who might want kind of their own little, almost tiny supercomputer in a way, and so it's important to be able to kind of compare. Is my lab, if I buy this expensive machine for my lab, how is it going to compare to maybe rent? I imagine at some points you can rent time on these massive supercomputers, and so like you can.
Oh yeah, yeah. They're usually most of them are government labs. Okay, and time on those things is given out with grants and stuff like that. So researchers have have access to supercomputing resources. They're a national resource.
Cool.
Okay, so that's the reason they exist.
Okay.
There's Department of Energy things that do things for military and stuff like that.
Right.
But yeah.
So it's good that we do this so that we can kind of compare to the really big guys.
Yeah. And those the same qualities that they use for supercomputers are great for a machine that you're a workstation that you're going to be doing. You're going to be working with. It gives you a really good measure.
Yeah.
And speak of supercomputing, I'll when we look at some numbers, I'll talk a little bit about how significant those performance numbers really are.
Yeah.
The two systems that I looked at is one is our 2U 4 GPU system that's sitting down at the office.
Mm-hmm.
That's on an older board. It's a dual Xeon Platinum system with 4 A100s in it. Nice.
Wow.
for what I'm looking at here, these CPUs don't really matter.
Right. Okay.
The other system I looked at is like, okay, well, I'm going to run this stuff since I finally figured out how to actually run this stuff successfully on the GPU. It was not trivial. Okay. Running these benchmarks on a GPU is not trivial, and NVIDIA kind of hides it from you. They might not like me actually posting. I don't know. Cool. No, they'll love it because it just shows how great the stuff is.
Yeah. Hey, controversy breeds engagement, so I'm okay if somebody gets grumpy about it.
Yeah, it's challenging. It took me a fair amount of work to figure out how to actually get these things to run. So, but the other system, this is my personal system that I'm actually sitting in front of right now.
Yeah, I see the Titans over your shoulder there.
Yeah, they're sitting back there. The reason they're sitting back there is because I have a 3090 in there right now, and I actually ran these benchmarks on the 3090.
Awesome.
And NVIDIA would definitely not like me talking about that.
Oh.
Although maybe they would. Because the 8100 just kills it.
I do remember a time where we weren't supposed to be putting GeForce cards for... so...
But, and I probably won't in the post, but I'm going to talk about it a little bit. But anyway, there in these charts, there's a bunch of other results. These things are standard benchmarks. They don't change very much. In fact, they don't really change. So it's a good benchmark over time. So you can test platforms and really try to get good results, and then you can reference those results as being a reference to that performance on that platform. So now we'll take a peek at this first chart. This is the HPL LinPack, and the chart here is in gigaflops. Okay.
Holy cow!
That's billions of floating point operations per second. The things that are in blue are CPUs. Okay, and the things that are in green are the GPUs.
Right.
It's
41,000 billion floating point operations a second.
Yeah, that's 41 teraflops. Okay, that's crazy. And you're talking about supercomputing. Okay, the first supercomputer where I consulted on did hardware testing for deployment of that machine. It ranked on the top 500 like 384th or something like that. It cost like over $3 million, and the performance of that whole machine was like 11 teraflops. Okay, and it's more like one of the A100.
Yeah.
And
wow.
It was a while back, but man, it wasn't that long ago, and people are still running that same software. Okay.
Wow.
So you have to understand the perspective here. The performance is just staggering.
It's
staggering. And this is in a single node.
Well,
That's one machine. It's got 4 GPUs in it. It's crazy. And this is full double precision floating point. That's the real deal. Okay. This is not, so that used to be an argument about GPUs. Is like, oh yeah, well, you can't do double precision performance. It's just no good. Well, Nvidia took care of that.
Yeah.
And in a big way. So yeah, it's absolutely stunning how good they are.
That's great.
Yeah, and and scaling is good. Two A100s up there is at 22, 23 teraflops.
Yeah.
One of them is almost 11 teraflops. It's like that supercomputer that I did. It would have ranked.
That's amazing.
One GPU. And then these Titan Vs, the two most recent GPU architectures that had high performance compute versions are the Ampere and Volta, and then that was Pascal before that. And you can see the doubling of performance here that I was talking about.
There's a comment from YouTube that I want to pop up here because I think it's relevant to what we're saying. Ron Kaplan on YouTube, he says, to be fair, the QBLAS is probably using low precision tensor cores underneath.
Okay, yeah, I probably the A100 has full, IEEE 745 double precision floating point.
Okay.
And this is true when we go to the Hpl Ai.
Oh.
Okay.
Okay.
And that that would be mixed precision. But yeah, he's got a good point there. But the thing is, this is the full benchmark. It's the residuals are fine. This is the full calculation.
Okay.
And so it's totally comparable here to the CPU. Now, okay, yeah, good point, Ron. I got some more numbers for you in here too. Ron Kaplan is I really admire and respect. He's doing great work with really cool stuff. And in fact, he tested on this machine. He set him up for him to do some testing on this machine. He's got some really nice code where he's using open ACC pragmas for accelerating his stuff in very highly memory bound code. Okay, so it was like really happy to have him on the system trying things out.
Cool.
But anyway, back to my point about the performance here. You can see with these Titan Vs. Now that was a Titan V. This was that was the desktop quote card that Nvidia did. This little puppy.
Yeah.
A few years back. It's only got 12 gigabytes of memory on it. And there was the V100, which was the Tesla. But this is, oh wow, what a really cool card. And it's got that the floating point, double precision floating point performance. But yeah, you can see that doubling of performance. You look at that one Titan V, 5 teraflops down here, 5.5 teraflops, you go up to the one A100 and it's 10, 11 teraflops.
That's so cool.
Okay. And it was the same way with going from Pascal. It was pretty much the same thing. They keep doing it and they say that they're not slowing down.
Oh, I believe it.
Okay.
And I know some of our audience may be edging more toward like the GeForce, the enthusiast crowd, but much like Intel's main business is not consumer CPUs, Nvidia's main business, or their main focus at least, is definitely not like their gaming stuff funds this stuff. Like,
yeah, it's the reason
they're
this stuff exists.
yeah,
is
they're
because-
all in on machine learning and
Oh.
and all of this stuff. They
They're
sell they sell video cards to gamers to fund science stuff like this. That is their real purpose.
Yeah,
And when if they're saying that they're not slowing down on this side of things, I 100% believe them. This is what they want to do to the core is science stuff.
Oh,
I know that kind of generalizes things, but this is where they want to dominate, and they are killing it.
and they're killing it. Yeah, yeah. There's a lot of stuff I could say about that, but we will.
We're not. Sometimes we're not allowed to.
revisit it.
We're not. We can't say too much.
Yeah, I've got to point out here that the top CPU result here is actually staggeringly good. That's the new Intel Ice Lake. Xeon.
Oh, nice. Okay.
Yeah, I tested that a while back, and I logged in. Supermicro gave me a login to go in there and fire up and run some tests on that, and of course, I did these things.
Yeah.
And that was the best CPU system I've ever tested. It's really, really good. Okay, and there's a lot of argument for CPU.
Mm-hmm.
Okay, there's still strong there's a lot of code that's where it's going to run, and CPUs are better than they've ever been.
Oh yeah.
But if you just looking at this right here, and in order to get that stellar GPU performance, the performance went up tremendously with the problem size.
Oh,
so this is very much benchmarking on my part.
Okay.
Okay, I did real benchmarking. I tried to get the best performance I could possibly get out of it. Okay, so day-to-day real world, your mileage will vary, as they say.
Of course.
But that's the same on the CPU side too. This is highly optimized. I mean, that's Intel one MKL optimized versions of the same benchmarks. Okay. But yeah, all the way down to my own machine, my little AMD 8-core machine, which I love, by the way. But I mean, just the magnitude of difference here is just it's insane. It's staggering.
Yeah.
Okay, so anyway, this blew me away, and this makes me say, like, okay, you really need to be running your code on the GPU. Okay, I mean, you need to make that effort to port your code, or if you're working on new code specifically, do it. And in my opinion, Nvidia has won this battle.
Sure.
There's been accelerators for decades.
Yeah.
And the only compute accelerator that's really been successful is the GPU. And Nvidia did all of the right things to propagate that and to move it forward. So there's a whole slew of new accelerators coming up, and some of them are going to be outstanding. I have no doubt. But man, it's going to be really, really hard to compete with Nvidia because they have set the bar so high.
Yeah.
And their development tools are really, really good too. So anyway, that's HPL. That's my favorite benchmark. I've got some performance. I want this to be reproducible. So yeah, that 4x8-100. This is a huge problem size. That's 144,000 system of equations being solved there. Okay, so yeah, it's really it's big.
And is that time in minutes or?
This time it's funny. It's kind of a funny measure here. This is more like it's more like seconds, man. It's insane. I mean, look at that bar, right?
Yeah.
Yeah,
so,
yeah.
So it knocked out 144,000.
But it is
problems.
In parallel. Yeah, I'm not sure exactly what wall time is.
Okay. We'll come back to that.
But yeah, I'll have to make note. I mean, it goes by pretty quick.
I mean, Yeah.
there's a bunch of time for the setup of the problem and a bunch of stuff going on. Once
Okay.
it starts cranking in on doing the solver starts cranking in, yeah, it goes by pretty quick. It's
Wow.
insane.
Okay.
But yeah, I've got one. I missed one here because I actually accidentally overwrote the output file.
Oops.
So I was like, oh man. But I want this stuff to be reproducible. So you see the main parameters that I've used here for the HPL DAT file. This is stuff that you need for setting the problem up. And so this is what I did. So these you should be able to get these numbers. Now the next one here, Hpl Ai. Okay, this is the mixed precision algorithm. And so this is using FP32. I'm not sure how this is structured. This is the first time I've ever really even looked at it.
Okay.
So I don't know all the details of this. But it's using the TF32. I think Ron is probably kind of referring to that. The TF32 is a 32-bit tensor cores. That's something that's new on Ampere, because the old tensor cores were 16-bit.
Okay.
So these are that's the tensor cores are kind of funny. I need to refresh really deeply into the architecture specs on this stuff now, because I haven't done that for years. But that provides stuff like essentially like vectorized fast multiply adds, so things that happen in like a single clock cycle on the GPU. So this is the kind of thing that like can double your performance, just boom, because you get multiple operations per clock kind of thing.
Okay.
And if you look at the number here for the this is the same problem. It's solving a big system of equations. I'm not sure how many equations I did on that. I haven't finished this post, so I don't have all this data up in here. But look at that number.
118 teraflops.
Yeah. See, so this more than doubled what was already that. If I put all of those other results on here, it would just like dwarf everything.
Yeah.
The CPUs would vanish.
Oh yeah, there's no point.
Yeah. So and the results I love this chart, and I love kind of actually how this worked out. These results are successful runs, solutions of that system of equations. Okay. The residual errors pass the benchmark test. And so it's a legit calculation. It's really solving the problem. But now you probably are not going to use that. You're going to use double precision in places where you like really need accuracy. If you use mixed precision, you use single precision, you have to safeguard your code. You have to be more deliberate about losing precision in your calculation. Accumulation errors, round off errors, things that disappear, or stuff that overflows and blows up. And I have a really nice example of something that overflowed and blew up.
I was going to ask about that zero.
That zero there. That's what and I'm not sure why this happened. This algorithm, this code is set. This is what Nvidia uses for testing on supercomputers.
Right.
Okay. So I mean, the very first thing I had to do was tell it that no, I don't have any Mellanox InfiniBand adapters.
Oh, yes.
Okay. So I mean, this is expecting to be.
I don't have any.
Yeah. This is what they run on their DGX systems.
Oh, okay.
That's their big heavy iron stuff.
Yeah.
So this is kind of funny running it on workstations. But for whatever reason, however this is structured, and I think it has to do away with how this is set up. I had to launch all these runs with MPI, message passing. This is what you normally run for distributing across a cluster.
Okay.
So I don't know how they have all this stuff set up, but when I used one GPU, the calculation would blow up every time. I mean, I went down to a very small calculation,
Yeah.
which was way smaller than would be reasonable to run on 40 gigabytes on these GPUs, by the way.
That's a lot. Yeah.
Yeah, there's 40 gigabyte and an 80 gigabyte version of these GPUs. Yeah, it's crazy. We used to think 8 was a lot, right?
Yeah. Yeah.
But anyway, the calculation blew up. The results come up. I get performance and all this, but it doesn't pass residuals, and I get not a number in there. So I mean, it's essentially overflowing or underflowing, or something is blowing up somewhere, and that's the kind of thing that happens. That's why double precision is the default for scientific computing. It's possible to use lower precision if you're very, very careful about any kind of precision loss.
Okay.
But man, it can really be hard to find places where you have numerical instability. And then, so the easiest thing to do is use higher precision. I've done calculations before where I've used quad precision.
Wow.
Okay, 128-bit floating point.
Wow.
Just because for numerical stability, because my code was so unstable, it's like, it's blowing up. So it's like, oh, let me try it with quad. Hey, it's working. But so in a way, I'm really happy that's in there, because it's an opportunity to point that out.
Yeah, no, that's good.
But for like model training and stuff like that, for big neural networks, this stuff works really great. And there's the frameworks and stuff are set up to where they're set up in a way that they're really not going to blow up on you very much.
Okay.
I mean, it's even common to use lower precision, like 16-bit or even 8-bit, which is just insane. Not so much in training, but 16-bit sometimes in training. But
okay.
It's I'm not so sure about that.
Okay.
But this is very good, and these results passed residuals. The Titan V did great. It worked fine with one GPU.
Yeah. So before we go on, what sort of just to kind of give context in a I suppose, like I'm explaining this to my mom, what sort of tasks, like or like real world examples could you give that this sort of Hpl AI would be how do I phrase this? Is this the kind of thing that would be powering, or would tell us a bit about the performance of like the Tesla autopilot sort of thing? Facial recognition sort of software, like what sort of real world example would this?
It's for actually like for training those models.
Okay,
because you've got large numbers of parameters, maybe millions, even these days, even billions of parameters.
Sure.
And they don't have to be all that accurate because there's so many of them.
Right.
You get this really strange effect, interesting effect with these big neural networks. And it's just the network kind of pick out generalized behavior, generalized matches to the input. And those parameters don't have to be super accurate. Okay, and in fact, when
enough.
Yeah, they have to be good enough. And it's because it's in aggregate that they have their effect.
I see.
And in training, you have to be very careful. But it's typical to take a model and you train it, and then you reduce that model. You try to make it smaller and smaller, and you drop precision and stuff like that. You get it down to where it's just an inference engine.
Mm-hmm.
So it's like your hot dog or not thing, right? It's just like you show a picture and it's like yes or no.
It can kind of give you a gauge, almost like I'm 80% sure that this is whatever.
Yeah.
Okay.
So that's that model shrunk way down, and it can be lower precision. You can optimize the stuff in a lot of ways to get it so it'll run on your smartphone.
Right.
But this is the measure of what you have to do to actually generate those models.
Aha. Okay.
This is where and that's the whole thing here.
I see. So this is building out how to determine whether it's a hot dog.
Yeah.
Then once it knows this is what I'm looking for in order to identify it, that's when it can become a smaller package.
Yeah.
Okay.
Yeah.
Okay.
Yeah. And scientific computing, I mean, the whole this whole approach with networks, this modeling approach, is being used in places. I mean, they're doing like protein folding prediction.
Oh yeah.
This way.
Yeah.
Which is really very, 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 it's a little bit controversial. It's very non-traditional, but there's enough data that it can be successful. These models can learn how to predict some scientifically very hard problems.
Yeah.
So this stuff is ending up on supercomputers. People are doing just amazing stuff. So it's I think it's a really good benchmark to have.
Yeah.
Yeah. And that this is more like, this is the kind of thing that's more appropriate on your gaming GPU.
Sure.
This is the capability that it has, is at this lower precision.
Okay.
That the FP64, that 64-bit floating point stuff, that's on the compute. That's on the Tesla.
Right.
That's on the high-end stuff. That stuff's not even on the Quadros. The Quadros are going to be more like down in this area too. Okay, now here to Ron's favorite benchmark, HPCG. This is a great benchmark, and Ron bugged me for a long time to start doing this when I tested hardware, and he was right. It was like, this is a great benchmark, this is because there's really important codes that are memory bound, and that's something you really need to know about a system. We've had customers that have bought, like the original Threadrippers with all these cores, and it's not any faster. It's because the code was memory bound and they didn't realize it. Yeah. And so they needed more memory channels. They needed more memory performance. And it was like, oh, dang.
Before we move on too far, I wanted to point out there was an interesting article that I thought about, and I forgot to share it with you earlier this year, and I think it's relevant to what we were just talking about as how these frameworks kind of get narrowed down to a more efficient and specific purpose. There was a pastry AI that learned to fight cancer. So, and again, I think this is one of those things where it's like, once it figured out a certain parameters, the clues that it was looking for in order to identify whatever it was trained to identify could be then used to another purpose. It was some store was using photos of different pastries so that they could charge their customers correctly. You just run a croissants and cakes or whatever through this thing. It could tell what it was, and would charge the customer appropriately. Well, it turns out that it was then kind of the quick thing. A system designed to distinguish croissants from bear claws has turned out to be capable of a whole lot more. And I just thought I wanted to highlight that as sort of, you start off with all of this sort of fuzzy data, and if you do it right, you can then kind of focus it down to a more particular purpose. And I thought that was really interesting.
Yeah, you can take these big models that have been trained on one task, and you can essentially go back into them and chop part of the model out, and then plug in stuff that's appropriate for your thing and retrain it on a new data set. It already has a really good general notion of how to recognize things.
And I think that's kind of what they did here.
That's exactly what's going on there, I'm sure.
Yeah. But go ahead. Sorry, I just wanted to mention that.
This benchmark here, again, this kind of rounds out that thing. We've got the double precision floating point. We've got the mixed precision, lower precision, floating point performance. And now we're looking at memory performance. And again, the memory on the GPUs, this is part of the expense of the GPUs. Mm-hmm. That memory is expensive,
right?
And it's very high performance. And on the A100, it's crazy high performance.
Yeah, it looks like it.
And yeah, and so this really gets shown off with HPCG, with this conjugate gradient probe benchmark. And this is reflective real world for a lot of applications. Okay, a lot of reality is here, and this is why, like Ron is like doing porting his code and run on GPUs, because he really needs this. And yeah, and again, the GPUs are just enormously performant. And again, you can see that doubling in this memory performance again. Yeah, it's crazy. It's crazy.
Yeah. Wow.
So that's the just kind of to round out what's going on, what's going into this post. I'm going to put I had an introduction there, what I was doing, and then I've got these results. I'm going to put stuff in here about how I actually did the benchmarks.
Yeah.
Okay, so I'm using the NVIDIA's HPC benchmarks containers on the NVIDIA NGC, their container repository. This is not a public benchmark. You need an account, and you need to use an OAuth authentication key to pull these containers. That's fine. I mean, because you should be a registered NVIDIA developer anyway, right?
I mean, who isn't these days? I mean,
yeah, there's millions of them, literally, really, there really is. But I'm going to go through how I did that, and how I got the containers. I used Enroute to do that, and this is just a clip of some notes that I was just command lines I was throwing up here. But I'll go through that, and then I'll also these little bits down here are the command lines that I ended up using to actually run the benchmarks. And I had to figure this stuff out because they don't have it in there. They have like kind of a macro to set up to run by default on a DGX system, which is not what I've got. So I had to mess with that quite a bit to actually get it to run right. But anyway, it worked great, and I would not have been able to do these benchmarks without their containers. I couldn't have put this stuff together and done it. So this is really cool. I was really happy to find that those containers that available on NGC. It was like, oh, this is great, because I really want to show. I knew how powerful the A100 was.
Yeah,
but I didn't have it. I hadn't done it myself. I've seen the numbers, but it's like, I want to run the numbers myself. I want to see it with my own eyes. Yeah. And yeah, it was really great. You notice I have a little thing here. What about the RTX 3090? I can tell you one thing about the 3090. For that double precision benchmark, those benchmarks ran on the 3090. It was like, whoa, hey, cool. I thought they would fail. I figured that there were some kind of flags in there that it would detect that it was not just the GA100 chip or right? BA1, whatever. But they worked, kind of. The HPL, the double precision one. Now on on the consumer cards, whatever, they do have double precision floating point capability, but it's very small compared to the single precision. So, for example, that RTX 3090, that was like 525 gigaflops.
That's still pretty good.
That's not bad. A few years ago, that's what I was getting out of a dual Xeon. A few years back, right? It was, and I was happy to get it. But you compare that to, what was it, 10, 11 teraflops.
Sure.
It's like over 20 times, the A100 is over 20 times more performant for the double precision.
Yeah.
So that's why you don't really use the GPU for the double precision. I mean, you can validate code there and it runs. Okay. I mean, I just thought it's like, hey, yeah, I got decent results there. I mean, it worked. It worked. I had the exact same problem with one GPU on the mixed precision code.
Oh,
I really wanted to see that one run on here because it's like, oh yeah, because this is where like the 3090 would do really pretty good. I would expect it to do very good, and I know that it would, but it failed the residual test. I saw what the performance was, and the performance was, I mean, given the calculation ran, the floating point ops would have been, it was like, oh yeah, okay, that's up there. But the result was junk because it blew up, but it blew up the same way it did on the A100 when I just used one card. So this is something to do with how this whole thing is set up, and I don't know. I don't know that if I can solve that with that benchmark or not.
Sure.
And in reality, it's like, yeah, probably want to run like, you know, a TensorFlow ResNet 50 or something like that to be comparing those kind of things.
Yeah.
And I'll do that, and I'll make that comparison. But then, the HPCG, I ran NVIDIA's optimized HPCG from that container, and it ran just fine. And it was something like, like 142 gigaflops that I got out of that. That's compared to like 227 gigaflops on the A100.
I mean, that's pretty good.
It's not. Oh yeah. Memory performance on these GPUs on like 3090, it's really good. And there's 24 gigs of memory on that 3090. That's a nice GPU, and it's going to have that, that nice single precision performance, that AI, that machine learning kind of training performance. Those are very good GPUs.
Cool.
Yeah, and you see my little conclusion there. The A100 is insanely great. It's like, yeah, it's really insanely great. I'm gonna try to make a little bit more discussion than that. Okay.
Sure.
But yeah, my main point here is, and I'm on my soapbox. It's like, if you're doing new code, especially if you're doing new code, you should be thinking about accelerated performance from the get-go. And a really good first step would be to try to write your algorithms, to write your stuff up with Python and like Numpy, and then try to use like PyTorch, use a machine learning framework then to make your life really pleasurable. They're great to work with. And whether you're doing machine learning stuff or not, they're fantastic for general scientific computing. And people don't know that. They don't realize that those frameworks are general purpose frameworks. Okay. So if you can do a NumPy implementation of your code, you can do that, essentially move that straight over to like PyTorch. And they're making that, they're trying to standardize that API. So that'll just be like seamless. It'll just go.
Awesome.
But you can do that, and then you can just tell it to, like, with one line, to say run it on the GPU. And so you can get that performance. You can see what that's really like. And that gives you a basis for further optimization. If you like, okay, this code really has to be done in C++ and whatever. This is your code to check your algorithms with and work on your optimization and do all that stuff. If I was doing code, a serious project, that's exactly what I would be doing. And there's a chance that I would not go any further than the NumPy implementation.
Wow. Okay.
I would write it up in PyTorch and run it and write up my papers and go on to the next project, right? And I would do it in a matter of a few weeks, probably, instead of a few years, like my doctoral thesis was. Fortran there, by the way.
Yeah. Wow.
But yeah, so you see what I was saying about earlier when I was like, I'm pretty excited about these GPUs.
That's great. This is amazing.
Yeah, I'm really, really pleased.
Wow.
Yeah, for an old guy like me, right, who's been doing computing for a long time, I look at this and it's just like, no way. I can hardly believe it, because I think back when I was running my, doing my quantum mechanics, doing my quantum chemistry stuff as a grad student, and it was like, oh man, we've got hundreds of thousands of times more performance now.
It's like
And
science
I could
fiction.
actually run that. I've run that same code that I did back then. I've written that up in Numpy and run it. Yeah, it works really great.
Oh, that's so cool. Wow. Man, I love seeing this kind of stuff and hearing you talk about it. It's always great.
Well, we did this one on short notice.
We did, yeah.
And the thing was, it's like, yeah, okay, just now do it because I've got something I'm really passionate about and I'm working on it right now. So I can easily talk about it. I can easily talk about Enroute too.
Sure.
Yeah, that's what's going on. And I haven't seen a single question.
No, there was early on
that really you think needs to be addressed. I'm happy. We're over already. We're over.
Yeah.
Already.
There was Ron had asked Ron Kaplan asked is there Mac support coming for Enroute?
Oh, that's a good question.
I would say probably not. Apple and Nvidia kind of know like each other.
I don't know. Enroute's a really nice project though. But I don't know. I honestly don't know. I don't see really why it wouldn't work, but I don't think they're working on it.
Yeah.
The focus of it is definitely Linux, and they're doing it. The guys that are really working on it are doing this in the context of resource managers like Slurm. Okay, and being able to schedule containers in that kind of environment, in a supercomputing kind of environment. But I know for a fact that it works in WSL on Windows. I've run it on there, and it actually runs with GPU support in WSL2 on Windows. But you have to be they've made advances on it, but you still at this point have to be in the Windows Insider Dev Channel build of Windows in order to be able to use GPU for compute within Linux on WSL.
Right.
That's really, really cool. And Enroute does run just fine in there. Cool. And Enroute runs fine in a virtual machine. Okay. You can run this on clouds. I'm not sure if you can run Enroute inside of an Enroute running container. Maybe not. I don't want to even think about that. But yeah, it works just fine in virtual machines. It integrates really, really easily with GPU, with the live Nvidia container, whatever. Yeah. You expect to see more about Enroute. It's really nice. It's really nice, and it's simple enough to use that it's even if you're doing stuff with like Docker or Podman. Podman is really a great alternative to Docker, and I'll probably talk about that. It's a lot more friendly for an end user because it runs in your space and not you don't have to have system daemons running or anything like that. Okay. Enroute is very simple because it allows you to take a container and create essentially a sandbox that you change root into that along with namespaces and stuff like that. So you own it and you're running in the container, and you can even actually go in there and edit that sandbox. You can from outside of the container, and they've got things like bundles, which I just started playing with. I barely even mentioned it on the post, and Jonathan called me out for it because going, hey, I was really wanted to get your take on bundles, and it's like, sorry, I haven't even really played. I tried it. It was like, oh my god, this is great. You can create these like Nvidia.run files, right, that people have seen. You can do this with Enroute with a container that you've got going, that you've got stuff set up to run. Do that and move it onto a system that doesn't have Enroute on it, and just run this run file, and your stuff runs.
Wow.
It's like, oh, okay, this is really nice. I'm going to be doing that for my benchmarks. I'm going to wrap all my benchmarks up in these bundles, so that when I go to do some new hardware, all I have to do is throw an Ubuntu server on the system, and then boom, run.
Oh, that'll be cool.
Yeah, that's going to be great.
Right on. All right. I think that about brings us to the end then.
Yeah.
Otherwise, you're going to give
I could
away
go
all your
on for
whole
another hour.
Enroute
I
thing.
could talk about
Yeah,
Enroute for at least an hour.
give away the whole Enroute talk before we get there. So yeah, we'll call it there. That definitely we're a little over, and it makes up for the Fire Gear and out the YouTube stuff, so we're fine.
Oh,
yeah, so thank you, Don, for giving us a rundown on the A100 stuff, and keep an eye out, audience. Keep an eye out for the full write up soon, probably Monday, I think is what you said.
Monday or Tuesday at the latest. Yeah,
sure. But you guys,
it should be a good. The post is coming out pretty good. I think it. Yeah, it's nice. I'm happy about this.
It was a good early look behind the scenes of the performance results and stuff, and it's of course it just mind blowing, like amazing. So that's really cool. And yeah, so thanks, Don, for taking time out of the day to give us this rundown. It's always so much fun talking with you, Don.
I enjoy it too.
It's so great. And thank you as well to the audience for joining us today. We do this every Friday,
Absolutely.
1 p.m. Pacific. We bring in our experts like Don and Matt and everybody else to kind of give us a rundown on performance, the crossover software and hardware. And we've also sprinkled in our support team and consultants, as well as outside experts who give us tips and tricks and advice for what they do. And so make sure you mark your calendars for that every Friday, 1 p.m. Pacific. And yeah, we'll see y'all next time. Bye.
See y'all.